Okay, that's what I got. All right, let's get started. Last week, we have practiced linear programming problems on paper. And we formulated the problem in both words and also mathematical expressions. This time, we are going to practice in Excel and see how we can use Excel to solve some linear programming problems that we formulate. You can find the materials for this lab. If you go to Canvas, there's an announcement I made in the first week, and the lab notes is linked here. In this session, we are going to practice the water supply problem in Excel. So I outlined the process under this tab, Programming with Excel. Here, you will find that programming with Excel is very straightforward. There are only a handful of steps. First, we set up the spreadsheet. Then we are going to enable the solver. Then we solve it by clicking some buttons and let the solver window understand what we want the program to solve. Then eventually we interpret the results. So as I listed in the shared notes, you can find the steps clearly outlined. However, let me just demonstrate here. Last time we worked on a water supply problem. So a growing city needs to determine the volume of water to draw in the future from 3 different sources. So these are site 1, 2, and 3. And as we formulated last week, there are a few constraints and one objective. The objective is to minimize the total cost of water supply. However, these are subject to 4 different types of constraints. First one is that we need to fulfill the demand so that the total water supply can never fall beneath the demand, which is 150 units. And the second constraint is about hardness. So the blended water should have a hardness level smaller than 1,200. The supply limit, each site has a supply limit, so it cannot supply us more water than its capacity. And the 4th type of constraint is that the water volume cannot be negative. So how do we use such information and supply it to Excel? First step is that we want to define the decision variables. These are the 3 decision variables, and initially they will be blank. So these 3 cells of in blue, they are decision variables. And after we define this, after we designate a few cells to be the decision variables, we are going to define the objective function. The objective function, as we formulated last week, it's a linear combination of the decision variables and the coefficients. As we can see here in the objective function, the total cost is the coefficient of cost times the volume from each site. Then we sum the quantity, the separate cost from 3 different sites. That's exactly what I'm doing here. I copied and pasted the coefficients of cost here, 500, 1,000, and 2,000. They represent how much money the city is going to spend per unit of water drawn from each site. Then how do we calculate the total cost? This should be very simple, as it's a function of the linear combination between the cost coefficient and the decision variables. Here specifically, I used a function called sum product. This is actually, it equals to the sum of products, which means that if I calculate it by hand, I would do this. To make a cell a function cell or a formula cell, we are going to type by first an equal sign. So without the equal sign, it's not going to be read as a function. So it's very important that for any calculation, we need to make sure we start the cell by typing an equal sign. After the equal sign, we supply the formula. So to calculate the total cost, it's going to be the volume from site one times the cost coefficient about site one. I do the same for site two and site three. As you can see, the calculation for total cost is nothing more than a summation of some products. As you hit the enter button, you will see that the total cost cell has a 0 value in it. This is somewhat confusing because here we have a blank decision variables. However, Excel will automatically or by default interpret blank cells as 0 in numeric value. That's why you see a temporary value shown as 0. However, this is going to change. For example, if I supply some volume that I thought possible, for example, 4, 5, 6, you see that the total cost is changed because this is calculated as a function of the decision variables. Here, those coefficients in green cells are constants, so they are not going to change no matter what decision variable values I provide. So this is how we can calculate total cost given any decision variable values. So I defined it as a summation of products. And I begin the cell by typing an equal sign. Any question here? You now understand how we can calculate the total cost? Okay, very cool. So using the same idea, we can do many other steps. Next, we are going to do the constraints. Just as how we defined the total cost, these constraints are also a linear combination between the decision variables and the coefficients. Last time in our practice, we formulated the problem after we summarize the given parameters in a table. This is going to be handy when we make the Excel spreadsheet. In addition to that, I just copied the cost coefficient. I did the same for the other information. They're reflected in this way. Remember that we transferred the hardness level constraints to a relationship expressed this way. So I transferred these coefficients to the Excel sheet. That's what you see here, -1,000 into -1,130. So after calculating this, we need to make sure that the left-hand side is going to be smaller or equal to 0, as this constraints requires. So how do we let Excel understand the constraints? This requires two components. First, well, actually three. First is the left-hand side value. This is represented here, LHS, standing for left-hand side. For example, in the hardness level, if I supply this set of coefficients and this set of decision variable, the calculated result as a sum product between these two rows is somewhere around -5,000. And this value is smaller than 0. So at this point, it satisfies the hardness constraint. If we look at the the demand constraint, what we were calculating is that left-hand side is simply the summation of the three decision variables representing the total volume we're going to draw from three different sites. And they can be easily calculated also as a summation of product given 1 to each of the coefficient. However, at this point, because the total volume is 15, whereas the total supply, the total demand is 150. So given this set of decision variable, it's not satisfying the demand request. That's why we need to change the value in decision variables, and this is going to be automatically done later by Excel. The other supply limit can be also calculated in the same way. Make sure that we supply the coefficient for each constraint correctly. For example, to represent the supply limit or the capacity from site 1, remember that it has a capacity of 25. 25 stays on the right-hand side, so our volume of the water to draw from site 1 is going to be smaller than this value or equal to. Then the volume is represented about site 1 represented by 1 times this decision variable, and that's exactly the X1 or site 1 volume. So if it makes it easier for you to understand, you can also type in 0 to site 2 and site 3 volume, because here on this line, we're only calculating the constraint about site 1. So that's why the coefficients about site 2 and 3 are both 0. You can do the same for site 2 and site 3 constraints. And that's how we can represent the capacity constraints. Are there any questions? Okay. Sum product, as I demonstrated earlier, is simply the summation of products. So when I calculated total cost, remember the process, right? So yeah, that's what sum product does. So for example, if I use sum product, remember we type the cell by first and equal sign. So sum product, first we need to supply arrays. Here arrays means like a range of cell. So here what I need to supply is the constraint, the coefficient of cost, and another array, that's the range of cell, that's the coefficient, that's the volume from each site. And this is exactly the value as I calculated earlier by using summation and multipliers. Yeah, sum product function is going to be handy for future calculations. So as long as you understand it's nothing but a summation of some products, then it's going to be fine. Otherwise, you will have to type in all the stars to represent the multiply operator and the plus sign to represent summation. Well, this just saves some time. Okay, now with this formulated, let's see how we can let Excel to solve this problem. For you on your desktop, possibly it's not the solver button here, as you can see, may not be enabled yet. What you need to do is to go to File. There's an option, and click Add-ins. There's at the bottom, you see a Manage drop-down menu. Select Excel add-ins and go. And there are 4 additional add-ins we can enable. And I'm just conveniently enabled, have them all enabled, because this time we are going to use Solver. And the future part of our course, we're also going to use the Data Analysis tab. So let's click Solver under the Data tab. This initiates a window called Solver Parameters. Here we're going to supply some arguments for the Excel solver to understand what we need to solve. First is the objective. Simply click the selection button and click the cell that represents total cost, because that's what we need to calculate as the objective function value. On my sheet, it's represented as the orange cell. Okay, and this is need to be minimized. That's why we select minimize. By changing variables cells in this tab, we need to select the decision variables. In my setting up, it's C3 to E3, the blue cells representing the decision variables. However, initially you can have blank inputs of all these cells. It's not going to affect anything. So how do we supply the constraints? This is done by using this menu. Well, let me reset all. Let me delete each of them so you can see the process of how we define constraints. Starting from a blank window, under subject to the constraints button window, we use add button. So first you see that to add a constraint, we need to select 3 things. First is the left-hand side value of the constraint. Second is the operator. So usually this is a smaller than or larger than or smaller than or equal to or larger than or equal to sign. So we need to select from the drop-down menu. There are a few other options. For example, if you require some cells to be integer, so it's represented by int, or binary, it means the value can only be 0 or 1. So here we select cell reference. To input the demand constraint, we click the left-hand side cell representing the demand constraint. Hit enter, then this left-hand side value needs to be greater than the right-hand side value, which is 150. That's a constant of demand. So our supply needs to be greater or equal to the demand. And then we click add. Then you see there's another blank window of add constraint. So that means we can add a second one. Do the same for hardness. We select the left-hand side value, then use a smaller than or equal to sign. And the right-hand side value would be 0. And click add. As you can see, it seems a very tedious process. What's helpful is that if we have the same relationship or the operator direction, we can easily select a range of cells. So we don't have to do this one cell by one cell. To select a range, simply click the select button. See that for all the supply limits, the relationship is represented by smaller or equal to sign, so that we can conveniently incorporate all these 3 constraints by selecting the left-hand side cells as well as the right-hand side cells altogether. So we can incorporate 3 different constraints in one step. Then after that, click OK. Now you see that I have 3 rows added to constraints, representing the 3 different components of constraint. First one is about demand, and second one is about hardness, and third one is about supply. Remember that here, although there's only 1 row representing the supply, there are actually 3 constraints corresponding to each of the 3 sites. And because we also want the decision variables to be non-negative, that's why I click this. I check this make n constraint cell variables non-negative. What this does is simply it adds a few other constraints. We can explicitly represent these non-negativity in this way. So to add the non-negativity constraints, we can do it this way. For example, non-negativity. So I use the same sum product function because this will simply calculate the volume of water from each site. And because this volume has to be greater than or equal to 0, so that the right-hand side values are going to be 0 for each of them. And in Excel solver, if we click the solver button again, we can add these non-negativity constraints, again, using add constraints. The left-hand side values are the volumes, and these are going to be greater than or equal to the right-hand side values, which are all 0, and click add. As you can see, there's a 4th row representing the non-negativity constraints. This does exactly the same thing if we check this make and constraint variables non-negative button. So this check does exactly the same thing as the 4th row of constraints. However, checking this while having this additional non-negative constraints never does harm because if we add the same constraints 1 time or many times, it's going to be having the same effect. And after that, we select simplex LP representing a linear programming problem and click solve. It pops up a solver results window. And by default, it keeps the solver solution in the cell. So after clicking OK, you see that the cell values are changed. So here in the decision variable cells E3 to E3, we see the values are now selected at 25, 74.6, and 50.4. These are the optimal solutions, or these are called the solutions to the programming problem. Because at this decision variable value, the total cost is minimized, and the minimized value is somewhere around 18,000, 188,000. So this completes our Excel demonstration. Any questions so far? Well, excellent. It seems we have just mastered another skill of solving linear programming problems with Excel. Okay, no problem. Once you come up with any questions, just let me know.
So I followed along.
Okay.
But I'm still getting an error.
What type of error?
So it says when I tried solving it that the solver couldn't find a feasible solution.
Oh, okay. So what's happening is that possibly some of the cell values are not defined as a function. As I demonstrated earlier, so one way to check is that if we click Formulas tab, and there's a button, Show Formulas. As you can see, if I did this, if you did this, you will find that if you define the cell successfully as a function, it's going to be represented by some function starting with equal sign. If instead in your cell, it's a constant, some value, some numeric value, then no, the function was not defined successfully. Can you now check and see whether you defined the cells as functions instead of constants? So for example, in my spreadsheet, the function cells are total cost and all the left-hand side values of constraints. And all the coefficients and right-hand side values of constraints are constants, represented by blue cells. If we didn't successfully define a cell as a function cell, it's not going to be changed, right? So remember last time when we formulate any programming problems, we need to formulate the objective as a function of decision variables, so as the constraints. So the left-hand side values need to be a function of the decision variables. That's very important. So after fixing that, you should be good if you follow all the steps. All right, with our first problem completed, let's work on a separate one. That's the grocery list problem. And it's your turn. Please start working on this grocery list problem. And you would need to do 3 things. Formulate the linear programming problem, first in words, and second in mathematical expressions, and third, solve it in Excel. Because in your homework questions, and also exam questions, you're going to see very similar questions like this. So why not we just practice here, and so we can help each other and understand what we do is correct and what options might be wrong. So please work in groups of at least 2. Yeah, ideally 2. Any questions? Okay, let me check. So please start working on this grocery list problem in groups of 2. And you will need to turn in a piece of paper at the end demonstrating the first 2 steps as well as the third step. So you're going to write down how you formulate the problem in words and also in mathematical expressions, and what are the solutions you find in Excel. All right, let me know if you have questions. Okay.
The same thing.
Or at least.
Right, and the second one is incorrect. But it should be. Yeah. Yes. However, these, coefficients of confidence, I think it's like they are, one stuff. They index the verb. Really are not.
One, I'm slowly, what is one? Yeah, and then I say that the minimum. Exponential.
So, if the solver doesn't seem to do any work, most likely you didn't successfully define the constraints or the object can never function. It's going to be a function on the left hand side. Yeah.
One book was.
The sum product for this.
No, because this is mathematics. Minimize. Minimize the cost of milk. While
Yeah, you have to read.
eating the milk requirement of.
All right. Yeah. So.
Ready and calling.
Starting with Worcester every day.
No, because the writing is value here. Correct. That needs to be. Oh, I see. And these coefficients. Here.
And as it is, optimal quantity would just be the maximum.
Take that table and put it in yours.
To express the protected and constraints for your quality of for example, I forgot to announce that as a bonus point for you, there's going to be some prize for the winner team. So, yeah, so let's see. How can we find a winner team? This should be the first team that reports to me with the correct answer of the Excel solver for this problem. So if you happen to almost achieve this step, then wait, are you already done?
Yeah.
Wait, is it that fast?
So, yeah.
Oh, okay. Are there other teams that have already found the solution? Oh, okay. No, then, okay. So, but the winner team is going to have two vouchers from our dining service. So you could earn a Panda Ball or Starbucks beverage or some Subway sandwich or Java City drink. So because you're working in groups of two, so you can have two vouchers and split between your two teammates. Okay. Hold on.
This is what I got.
It appears we already have a winner team. So,
Thank you. Move on. I just follow the same steps you did on this one.
Yeah, but like, with the, but like,
It's like copy and paste. Yeah, and then they copy and paste this one, and then I just refilled it. Welcome. Jerry, we didn't. Wait, you the folder. Oh, this is snaps. E for you. We need to get It's not as so you to be one more. Not be very I got it from Gary. It says no, reconsider, just for ask the Okay. Why did that? I think I already saw it.
All right. Are you almost done with the problem?
I'm taking a while.
Well,
You do some product, do we need to do, like, this is enough, right, or do we need to do every?
yeah.
No, what I'm saying is like, for each array, right, do we need to do? How do you do it, like, show me your, like,
So for the following rows, you
No,
do
to-
the same.
oh, to do the same, so we only do like, for each row, we only do like this one and this one, this one and this one, this one, like that.
Mhm.
That's it.
Exactly, because it represents the value we need for the left-hand side values of the constraint, right? So. We do it.
Okay.
Right. Any progress? Are you almost done with the problem? Need any hints? My original plan was for you to switch your answers between teams so you can grade each other. But I'm not sure whether we have enough time for that part.
I'm loving it. Move so hard. Good.
Oh. Perfect. Thank. Yeah. I think, yeah, the result is good.
Oh, what about like some of the constraints or not?
It's fine. 8, 6 minutes. So 2.8.
All right. How about we work on this together and you can see how I would, if I were to do this problem, what that looks like. And what's very lucky is that one team has almost a perfect answer, so it seems I could just copy and paste. So first, we want to make sure that we express it in words in a way that first we define the decision variables as the pound or liber of this that xj represent liber of what are the three things? Milk, right? There's also these, and what's the third? Oh, an apple. So we have x1, 1, 2, 3 defined again, just like what we did for the water supply problem. And the second is that we want to define the objective. In words, it's going to be minimize spending. And in mathematical expression, it's something like this: minimize z as a linear combination of the objective of the decision variables. And this is going to be 1 times x1 plus 2.5 times x2 and 0.75 times x3. These are the cost coefficients per unit of food. And third, we need to define the objective function, the constraints. So these are subject to, there are 4 constraints because we have 4 different types of nutrition that we need to meet the minimal threshold, right? So all of these 4, we have a greater than or equal to sign. And on the left-hand side, we're going to express the our nutrition facts out of the decision variables. This is done by another linear combination or some product between the coefficients and the decision variables. So from from milk, we can derive 40 units of a protein. Right, this is the idea. And the right-hand side will be the minimal protein we must consume in a week. So we do the same for the other 3, and the last one would be 30, x1, 3, x2, and 60, x3. And the right-hand side values are 80, 60, 50. And each of them has this greater than or equal to sign. So this completes the formulation as we have decision variables, objective function, and 4 constraints. And remember that we also want to add a few others like x1, x2, and x3 needs to be greater than 0, so the non-negativity. And with that, we can use the same Excel layout and solve this problem in Excel. And for the answer, you will write something like the optimal solution is x1 equal to some amount, x2 equal to some amount, and x3 equal to some amount. And these are calculated in Excel. And we can, of course, calculate the objective function value at the optimal solution. And this is going to be a z value calculated as a result of the solution.
Sorry, is it objective is to minimize the cost as well, right? For optimal options, minimize costs.
Yep. And yeah, for our practice, particularly, I asked for x2. So,
It's 0.
but yeah, x1 and 3 are side products.
Can I ask? So you what I did and let me know if it's right.
Sure.
Here?
Yeah.
Thank you.
Hold on a second.